Let us now finally look at two matrix operators, the trace operator and the determinant of a matrix. The trace operator returns the sum of all diagonal elements of a matrix. In other words, the trace of matrix A is equal to the sum over all I elements AI, I. The trace operator allows for writing the Frobenius norm of a matrix without summation. If you remember, before we have written the Frobenius norm as the summation of all squared individual elements followed by the square root after the summation. Now we can simply write this as the square root of the trace of A transpose. The trace operator is also invariant to the transpose operator. That means if we transpose the matrix, the trace stays the same. That makes sense because the transpose operator just mirrors the matrix elements along its diagonal. So the diagonal will stay the same. And finally, the trace of the product of square matrices is invariant to cyclic permutations. That means we can cycle these three matrices through here. We can take this matrix C here and put it in front of A, and we get CAB. And then we can take this matrix B and put it in front of the matrix C, so we have BCA. And the trace of all of these three matrices, which are themselves products of three matrices, A, B, and C, is the same. The determinant, in contrast to the trace operator of a square matrix, is equal to the product of all eigenvalues. In other words, the determinant, written as such, is equal to the product over all I, lambda I, where lambda I is the ith eigenvalue of the matrix A, as we have defined it before in the unit on eigenvalue decomposition. The determinant can hence be thought of as a measure of how much multiplication by the matrix A expands or contracts space. If we take some vectors describing points in 3D or higher dimensional space, and we multiply those to the matrix A, then they will either contract towards 0 or expand away from 0. And the determinant can be thought of as a measure of how much this effect takes place. In particular, if the determinant is 1, then the transformation is said to be volume preserving. The volume described by the input is preserved when applying this matrix A. And on the other hand, if the determinant is 0, then space is contracted completely along at least one of the dimensions. It collapses along one of the dimensions, causing it to lose all of its volume, collapsing all of the volume to 0 along at least one dimension. In other words, the matrix is singular or rank deficient in this case.